Hello everyone, welcome to a new video on group theory. Let's go and solve this nice interesting problem. So we have, this is the problem, let G be a group. So we have our G is a group. Okay. And let little g be an element of G. And we have little g an element of G. Then it says define a function little phi of g from g to g by little phi of g of x equal gx g inverse for all g in g. Okay, there's a lot of g over here. I'm going to write it down. So we have a function which we call a little phi of g. You'll see this notation a lot of times. It's very useful in abstract algebra. Anyways, we have this function that is a mapping from the group G into itself, and is defined as little phi of G, little phi of G of x is equal gx G inverse for all element x of the group. Okay, and now show that little phi of G is a bijection. We have to show that little phi of G is a bijection. Okay, it seems really interesting. There's a few nice little points that we have to talk about. So let's go on and write our proof. Okay. We have to show that a function is a bijection. Okay, so we already know that our proof is going to be divided in two parts. The one part that we're going to show that is injective, so that is one-to-one, and then we have to show that the same function is also surjective, so that is onto. Okay, so let's go on and pick one. So let's try to prove as a first thing that is injective. So let's prove first injectivity. Okay. First thing, what do we have to show? Remember, injectivity is proven by you have a function like normal way. Okay, we have our function f, and we have two members of the domain x and y. We have to show that if we assume that f of y is equal to f of x, and then we have to show that this implies that y is equal to x. In this case, our function is injective. Okay, so let's cancel this. Okay, all right. So let's start with, let's put two elements in a domain. Okay, so let x and y be element of the domain. So we know this is our domain. Okay, that's from the domain to the codomain. In this case, they are the same. So the only thing that we have to make sure that everything is in the group. Okay, so let x and y be element of G. Okay, now assume, as we said before, that our function f little phi of G of x is equal to little phi of G of y. Okay, and then we have to show at the end, if we can, if it is injective, we're going to have the x equal y. Okay, so let's see how this works. What is little phi of G of x? So it's defined right here. Okay, so this is G x G inverse is going to be equal to, since this works for all the element of the domain, so this is going to be equal to G y G inverse. Okay, all right, this Now we have a very easy step to do. We already know that in the group left and right cancellation laws hold. So for the left cancellation law, we can cancel this guy, and for the right cancellation law, we can cancel this guys, and we have in fact the x equal y. Okay, and we proved that little phi of g is injective. Now let's prove surjectivity. Okay, what do we have to prove? We have to prove that for each element of the codomain, let me go back right here, for each element of the codomain, there exists an element in the domain such that the function little phi of g of an element here is the element I picked of the codomain. Okay, in other words, so in our specific case, we have to prove that for all y, for an arbitrary element y in the codomain, this g we saw before, g is the domain of the codomain. Okay, but this represents in this particular instance the codomain. For each element y in the codomain, there exists an element x in the domain. I know they're the same, but this is codomain, domain, such that little phi of g of x equal y. Okay, this is what we have to prove. We have to prove that this element, okay, of the codomain has a pre-image in the domain. Again, let me, if you don't mind, let me cancel this. Okay, so let's start by choosing an element from the codomain. Okay, so let the element y be in the group. Okay, we know that our codomain is G. Okay, now we claim, we have to show that, let's say we claim that little phi of G of x is equal to y. Okay, now let's find an x that will do the work. Okay, and let's make sure that we got the right x, an x that is let's make sure we're not doing any illegal move. Okay, so first let's reason a second over here. Again, so what my little phi of g of x, what it does is it multiplies on the left side by g, my element x, on the right side g inverse. What if I want to cancel this, guys? Okay, so I would multiply this by g inverse and this by g. In this case, I would have that my function of x is equal to x. Okay, so how about I want a y over here? So let's do this. Now we do let x equal look at this, g inverse y g. Okay, be an element of the domain. Okay, and we're going to show that little phi of g of x is equal to y. But before this, let's make sure that this statement is true. Okay, we stated that this element here, the x, is in the domain, so x is in G. Okay, let's reason a second. Is this really in G? We know that y is in G. Okay, we put it. We know that for the statement at the beginning, that G is also, little g is also an element, okay, of the group. Recall that if an element is in the group, then its inverse is in the group. So we know that G inverse, y, and G are all elements of G. And also we know that the group is closed under the operation. So this, all those elements are in the group, but also all of them operated together, there are in the group. So we are correct. Our element x, which is G inverse yg, is indeed in G. So now we will show that f little phi of g of x is y. Okay, so how we do? Straightforward. We say again, f little g of x is equal phi little g, sorry I said f, phi little phi of g of this guy, G inverse yg, okay, which is equal to, what does the function do? It operates G on the left, G inverse on the right. So you have G inverse, and you have this guy in the middle, yg. And look at this, these are inverses of each other. They're the identity, so we can just cross them out, cancel out, and we have little phi of g of x is indeed equal to y. Okay, and we're done. Our proof is complete. Remember, let's summarize. We had to prove that it was a bijection, that a function was a bijection. We had to prove injectivity. So we assumed that the function of x is equal to the function of y, where x and y were element of the domain, okay? And then we show that x is equal to y. Then we proved surjectivity. We had to prove that every element of the codomain has a pre-image in the domain. So for each element y of the codomain, there exists an element x in the domain, such that the function of x is equal to y. And this is what we did. And remember, this passage is very important. We said, let our element x be an element of the domain, and we'll prove such and such. But we had to make sure that we were saying something that was true. In fact, sometimes I cannot prove this, and the function is not surjective. This is the most important part, is to find an element that, with manipulations you get to your element y, but also you need to be sure that that is the case, that the element is really an element of the domain. Okay, and we show that when x is in this form, little phi of g of x is actually y, and we proved also surjectivity. Okay, I hope you enjoyed and I didn't confuse you. Thank you for watching. I'll see you in the next video.